my friends. So, okay, good morning and thanks for being here. Today we start with Brian page about jet physics at EIC.
All right, yeah, so I'm going to give an experimental view of jets at an EIC. Probably most of you have heard bits and pieces of this talk before, but I want to make a couple more kind of emphasis points on a few things. I will just say, so Elka referred to in her opening remarks that jets at an EIC was undiscovered territory. I prefer undiscovered country, which is probably the second best Star Trek film.
Okay. That's a cool logo. We should keep that.
Yeah, I worked very hard on this. Okay, so getting into the outline of the actual talk. So I'm going to start off with just some basic comments on jet PTs and radius considerations when we do our jet finding. Then I'm going to go into a more concrete example, looking at an example of leading order Dijet ALL measurement to kind of see what we can do with jets, and also show some of the kinematics in a little different way. I'll talk a bit about substructure. I think Felix is going to touch on this as well in his talk. So I'll cover some aspects and Felix will cover others. And if there's time, maybe I'll bore you guys with some detector discussions, since I am an expert. Just real quick, relevant subprocesses I'll be talking about. The resolve process, where we have the photon splitting into a hadronic state, kind of the higher order corrections to the DIS process, QC Compton, and photon gluon fusion. These guys will give us our harder jets and Dijet events. And I actually won't talk too much about the actual leading order DIS process, which normally just results in one jet, a beam jet. Just real quick, so all of this is simulation. So we do electron-proton events generated at, unless I say otherwise, root S of 141, which is kind of the envisioned maximum center of mass energy for an EIC, corresponding to 20 GeV electrons on 250 GeV protons. This is done in PYTHIA. Cuts on elasticity, again, unless I specify otherwise, looking at the anti-KT algorithm with an R of 1 in the bright frame. And then the inputs are all stable particles above 250 MeV within our envisioned detector acceptance of plus minus 4.5. All right, so the main question, kind of topic I want to bring up, and hopefully we can have some discussion on it, is the issue of how low we can go in our measured PTs. So, so here I show the jet PT spectrum coming from the photon gluon fusion process for these two root S's and these two Q squares, 1 to 10 and 10 to 100. So, I mean, as an experimentalist, I can look at my input, I can run a jet finder on it, and I can find an object to whatever low PT I want. The question is, how low can we go and still be useful? How low can we go and still have it under control theoretically? I think this is an important question because of, if you look at these guys, these are very soft spectra. And so if I place a cut at 10, I'm already getting into the realm where, maybe jet measurements just won't be competitive statistically. So here, these are normalized. This is counts per 1 inverse femtobarn. So if you know, if we collect one inverse femtobar and get 10,000 jets total, you know, is that enough to really do any measurements on? And it gets worse if you go to lower root S's. And so this is kind of, these are kind of the max energies for an ERIC and a J-like. And if we talk about now going to EA, where the hadron energy is lower, again, now we're really hit. If we have a root S of 90 or a root S of 40, you know, now we're talking in the some thousands of jets if we have to place a cut, say 10 GeV. So the lower we can go in PT in a controlled way, the more likely that jets will be an actual useful measurement at an EIC. So this is one of the questions I think is rather important. So here we see the same thing now just for dijet mass. So here I require one of my jets to be above 5 GeV, one of my jets to be above 4, and then I ask that they be separated in azimuth, and then I just plot the mass again for the 2Q square ranges and the several energies. Again, this is from the photon gluon fusion process. Same kind of sorting, you know, the lower we can go. If we start placing cuts on jet PT that are too high, we cut off a lot of our statistics. Another thing to keep in mind when we're talking about jets in EIC, and Elke I think touched on this as well, is particle content. So these jets are relatively clean. They're not an abundance of particles within the jet. So in the context of like a substructure measurement, these kind of considerations could become important. I'll show, I think actually the substructure stuff is looking pretty good, even with the relatively low number of jets, or of particles. So I'll talk about that a little bit later. Another thing to think about is what kind of radius we want to consider. So here we see for the photon gluon fusion process at a Q square between 10 and 100, the dijet mass versus the Partonic root S. And so the root S should give you the mass. And so here you see the reconstructed mass versus root S for 3 different radii. And as you see, as you reduce your jet radius, this locus kind of moves off the diagonal. So what you're doing is the smaller your jet radius, kind of the less of the energy from the hadronizing parton you're catching, and so you're underestimating the partonic quantities as you go lower. And so for an analysis where you want to capture the partonic information, maybe it seems that the larger radii are better. You're capturing more of the information. You're reproducing more faithfully your partonic quantities. Other analyses may be different. If you're doing a substructure analysis, you're doing some other thing. You know, maybe there are other other considerations that come in. You want to use a smaller radius.
Just your plot of the slide before of the particles, that was for a radius of 1.
Yes, I'm sorry. Yeah, this is for the radius of 1.
Fine.
Also to keep in mind, this isn't charged particles. This is anything that's stable. So every pi 0 that comes into my jet is 2 particles in this plot.
Which
So-
is fine because we count photons normally.
Yeah,
If
yeah,
I
but
go,
I
of
just,
course, to a radius of 0.4 and I'm at maybe a PT of 6, my 6 particles, which you call now a stable constituents of the jet, become maybe something like 3 or 2.
yeah, so I think,
That is.
I don't have the plot, but I think if you look at, say, at an equal PT for a radius of 4, I think you can kind of just shift this curve down by an average of like 2.
That's what I was
something like
roughly kind of,
Yeah.
yes. But if you go to the next, I think that is something which needs to be kept in mind if you shrink your radius and your number of particles. Right. If you go to your next slide, of course, what you see also with a radius of 1 is that you get these tails to high masses, which of course come from that you have the underlying event inside your jets.
Yeah, so I actually didn't put the underlying events stuff in this talk. So I mean, EP events are going to be relatively clean. So in like a hadron collider environment, generally when you're looking at jet radius, kind of what you're optimizing is just that. You know, you want more, you want a larger radius because it's capturing more of the fragmentation from the parton. But the larger your radius, the more underlying event you sweep up as well and distort your signal, I guess, in some way. And so there's usually some kind of optimization that goes on between those two effects. Here, I knew at some point, I haven't looked at this particular plot in a while. I knew at some point what this was. I'm not sure its underlying event as much as I want to say it is, in some sense, a misidentified, maybe that's not even the right word, but, you know, so if I have my 2 partons coming off from, you know, my photon gluon fusion event or whatever, and I find 2 jets that correspond to those 2 partons, that's all well and good. If there's a 3rd jet in the event, and I happen to take that one that's not associated with the parton so much as the other jet in my Dijet event, you're not going to reconstruct the mass the same. So I think these actually might be more mismatched guys. And when you go to lower radii, you're biased towards a harder fragmentation inside of your jet, fewer particles that are higher PT. And so I think that kind of reduces this high mass tail a little bit. But yeah, I made these plots quite a while ago, and I know I looked into these tails, but now I think that was the explanation. But
So why does S have? Why should that agree with the Dijet? And why is that a criterion? I mean, it doesn't need to agree with that. Dijet doesn't need to be set.
I think, I mean, that's kind of the mass energy scale that comes in, right? And so if you have, you know,
not everything has to end. Right.
True. I think if you do look at this, you know, if I go into the PYTHIA record and find the 2 outgoing partons, and then I say, you know, I can just look at those, you know, I don't run a jet finder, I just look at the PYTHIA event record and say, I'll form a mass, you know, the invariant mass of these 2 particles, and plot it versus root S. It is basically a diagonal line. It does correspond, at least in PYTHIA. There's a pretty much one-to-one correspondence between those 2.
Is that because it's meaning order things are? So you have like analog.
So that depends on what you call analog effect, because of course EGF is an analog in DIS. and QCD content as well, and there's Proton shower. So it's not an NLO matrix element, if that is what you want.
I think this is terminology. I mean,
yeah.
Content is the leading order for this process.
Was it? Yes, for Dijets, yes.
So that the movement is another Gluon, right?
Yes.
But you have like an additional shower or something. You need some
Right.
radiation.
Yeah, I mean, that's why this isn't, you know.
For large radius, we have those small radius. That's on the bad side. I don't see what your criteria for using a small like large radius. Only say whatever it's possible.
Yeah.
Yeah, I'm just saying, you know, so if you want to reconstruct, you know, some Partonic quantities, so I'll show, for example, you know, you can reconstruct the momentum fraction that the photon contributes to the reaction. For example, if you're looking at a resolved process, you can reconstruct that by, you know, combining your Dijets in a certain way. The same for the Quark coming out of the Proton, Gluon coming out of the Proton. So if you reconstruct those not as well.
The labeling is that root S hat on the lower axis.
Yeah, I'm sorry.
Mass square.
Yeah, so that's mass, that's root S. Sorry.
And so then in the derivative calculation would have the Dijet mass, of course, smaller than root S hat, right? So that would be something lower corner, right? Lower. So whatever is up there. Interesting.
Yeah, and maybe, you know, maybe this afternoon I'll go back into my code and look at these guys again. All right, so now I want to switch gears a little bit and talk about this this analysis we were thinking about, looking at Dijets to take the photon gluon fusion process and get a look at delta G. So here, just kind of an introduction, seeing as this is the Helicity week. So the EIC will primarily measure delta G by looking at scaling violations of the G1 structure function. So here we see the current world's polarized data from fixed target DIS, and then this is what the EIC is expected to provide along with our current uncertainty. So you'll see it will greatly expand our Q-square range and S. But we can also think about another way to do it, where so the photon gluon fusion process, this guy here, you're getting a gluon from the proton, splits into a quark anti-quark pair, which interacts with your virtual photon, and so this guy will generally give you a Dijet type event, you know, two quarks going out. So the QCD Compton will as well, which gives us information on the quark. And we also have this resolved event guy, which is basically the DIS equivalent to 2-to-2 scattering, where our photon behaves hadronically, provides some parton with a momentum fraction, which then interacts with Quark or Gluon from the proton and gives you a kind of 2-to-2 scatter. So we have a paper out on actually using Dijets to measure this and tell us about the structure of the polarized and unpolarized structure of the photon. So this is kind of the flip side of that. We want to suppress this process and look at this guy to learn about the gluon coming from the proton. So just a real quick word on kinematics, just at leading order. for this type of process. The momentum fraction of your proton is given by this relation, which can be rewritten in terms of kind of the beam parameters and our Dijet mass. And so just as a benchmark, if we remember, maybe our lowest mass range is something like 10 for Dijet mass, and our beam parameters, S is 20,000 for the highest root S's, Y is like 0.95. We can expect to get down to an X of about 5 times 10 to the minus 3. So kind of circling back a little bit, if you remember, we want to try to suppress this resolve process. Of course, this really helps out. You just go to larger and larger Q-squareds, and this process becomes less and less important. It dominates at very low Q-squareds in the photoproduction region. But there is some, at least we find in our simulations, there is some that sneaks in even at larger Q-squareds, which we'd like to suppress. And you have to remember, so in terms of the total cross-section, this resolve fraction is very, very small, like less than 1%. But because we're forcing ourselves to look at events with Dijets, it's a very biased sample. You get basically almost zero from the leading order process, and everything else kind of comes in. So we do see some that sneaks in. We want to get rid of it. How do we do that? As I alluded to before, we can construct this X gamma variable, which is basically this guy, the momentum fraction that's coming from the photon. And so for a direct process like photon gluon fusion or QCD Compton, the photon behaves in a point-like way, and so X gamma should be 1, whereas here X gamma can take a continuum of values, which is kind of what you see here. So this is the reconstructed X gamma. This is the formula here, so it's just somehow the energy is the transverse mass of the jet times e to the rapidity in this combination. And so you see this plotted here, and so you see the direct processes in blue, green, and there is some Dijets from DIS that sneak in, where basically you have the target has enough of a kick to provide a second jet. But you see these guys are clustered close to X gamma of 1, whereas the resolved here in red is much more spread out. So if I put some kind of cut at X gamma and only consider X gamma close to 1, I really reject these resolved guys in favor of my direct processes. And so here you see how well we reconstruct X gamma and also the momentum fraction coming from the proton, so reconstructed versus true. And you can see that this, again, with a jet radius of 1, this does a pretty good job of recovering.
Sorry, I don't understand something very basic. So resolved photon Q square is non-zero.
Yes.
Then why
So I mean, I always get asked this question, and it's.
What was the question? Can you speak about?
No, the Q square is non-zero, so I thought the
So
resolved photon is a variable only for photon production.
So see.
But I mean, there's got to be some kind of. It's not. It doesn't exist only at a Q square of 0. It's got to have some kind of distribution, right? And what I'm saying is,
but the Q square is even 100 Q.
Yeah, this is my concern as well. I think there was work effect on the structure of virtual photons. However, that certainly went, few jets squared at most. But I mean, between 10 and 100. it seems to me there would be little motivation to have anything like a resolved photon contribution, right? Because after all, the resolved photon picks up processes where photon splits collinearly almost into a bar pair, and that's what you need to, theoretically speaking, factorize into that resolved contribution. And with large Q-squared, you just don't have that. I mean, there's no
So I mean, PYTHIA certainly has like a parameterization for the cross sections for this, and I mean, you know, it may be that the tails as you go up to larger and larger Q-squareds, you know, are uncertain. But
okay. One thing is also your plot, in addition, is dominated by Q-square of 10.
yes,
Let's so to say 10 and 100.
it's not flat between 10 and 100.
It's not. So what you see is.
I have another bin that's 100 to 500.
And then it is gone. So it is really, as Brian says nicely, it is the tails. And so if we would kind of choose, it probably would be better to choose 1 to 10 for this, because that's where the cross section is, because here you look into the tails. Absolutely.
And so again, I mean, like I said before, we really are looking at the tails. If I plotted, or if I just showed, so this is like 20 million events or something that I generated total, you know, we're talking about less than 1% from the resolved process. But because you're looking at a Dijet, it's an extremely biased sample. You know, you're really biased against the leading. You know, you're biased against, you know, 95% of your cross section, and so you really are kind of looking at the tails here. And you know, so how well that parameterization in PYTHIA for how that cross section dies off goes, you know. Yeah, maybe it's not really there, but it just you know, the way that it's parameterized kind of brings some in.
But it's not possible to just look at the really low Q-squared bin, or is it? I mean, you could,
yeah, that can
right? I mean, this would increase the weight much more.
Yeah.
Okay.
Yeah. So I mean, that's you know, I don't have these. I don't have them in this talk right now, but yeah, I have looked at Q-squareds down to like 10 to the minus 5, which is kind of the limit that we can go to and still detect our electron in a low Q-squared table. Okay. But yeah, then you see a greatly enhanced resolve contribution. Okay. So it behaves like you think it would, as a function of Q-squared, whether or not the yield in this high Q-squared tail is modeled exactly correctly with PYTHIA.
I think it's more of a proof that it's a method to reconstruct the gamma and suppress anything which is not a direct photon contribution. Works nicely.
And I mean, yeah. So you know, when we turn on the machine, we look. I'm an experimentalist. I'll just look at it and see what the contribution is. And again, as Elke said, this kind of method, I think, will will help us. You know, we can just really see, you know, if we reconstruct X gamma, do we see a tail as a function of Q-squared? But this is this is currently what we get out of PYTHIA, and so it's something we want to suppress. This method does that. So a quick word on how we actually get an asymmetry out. Of course, PYTHIA doesn't include Parton polarization effects, but we will just weight our event sample according to this formula here, where we have the leading order Partonic asymmetries A hat, and then we'll have two terms describing the polarized, non-polarized photon and nucleon structure. And so for simplicity, what I'm just going to show, I'm just going to, from now on, ignore the resolved component. So this guy will be 1, again, because it's now I'm only looking at direct processes. And then this guy will give us our information about the the polarized and unpolarized proton structure. So I use DSSV14 and NNPDF 1.1 for the polarized guys, and then the corresponding unpolarized sets that those two collaborations use to extract. So I think for DSSV it's MSTW 2008, and NNPDF is NNPDF like 2.3, I think I used. And so here you just see for all the different sub-processes kind of what the weights look like. And so this is what we get. So this is the ALL as a function of mass, of the Dijet mass, for the QCD Compton process and the photon gluon fusion process for the two different PDF sets. And so you see that the asymmetries for the individual sub-processes become quite large, up to roughly 20-some%, but they're opposite in sign. And so when you combine the sample, actually they cancel quite exquisitely. So this is another game we were thinking about playing. So this is kind of leveraging our the fact that we can also look at the momentum fraction of the parton coming from the proton, and we expect the photon gluon fusion process to peak at lower values of X than the QCD Compton process, and so that's what you see here. And so you can think about maybe drawing regions in this X proton variable to look at enhanced, to look at regions where the photon gluon fusion or your gluon contribution is enhanced. So that's what I'll jump through real quick here. And just another note on the kinematics. So this is kind of the relevant kinematic plane. So here we have our XP variable plotted versus Dijet mass. And so you'll see as I make my cuts in X proton, I'm restricting my mass range in such a way. And so if we bounce through the plots, you see how things change. And so what I plot here as well, again, the DSSV14 and NNPDF curves are pretty much on top of each other. I also show the current uncertainty from the NNPDF group, represented by this blue band. This is just the uncertainty from the PDF. And I've scaled my error bars here. This is purely expected statistical errors based on this formula, as well as 80 and 70% beam polarizations. And this is for integrated luminosity of 10 inverse femtobarn. So then I show the same thing again, the same 4 plots for a Q-square between 1 and 10. You see the same general behavior. And I also show what we can get with a 50 inverse picobarn or inverse femtobarn sample. So you can see how the error bars decrease. The same thing for, so now this is again 50 inverse femtobarn for a Q-square between 10 and 100. So you can kind of see how things change there. And so maybe the takeaway here is, so these blue bands kind of represent our current knowledge on the polarized PDFs. Of course, the inclusive measurements from an EIC will greatly shrink these as well, these bands as well. So I think this will be a statistically challenging measurement to place constraints, but Another thing we have to keep in mind is that this kind of analysis will have very different systematics from an inclusive analysis. And so I think it can still be important as a cross-check and as a way to kind of look at somewhat orthogonal sets of systematics, which is always a good thing. So just quickly, again, now about energies here, I just want to make the point. So everything I've showed has been for kind of the maximum root S of 141 GeV, and that kind of sets. If you remember, I showed that leading order formula about the kinematics. That kind of sets how low you can go in XP and the mass range that you access. And as you go to lower root S's, these curves kind of back up, and you restrict your lowest XP range as well as your mass reach. But if this is really going to be, if we want to try to wring out as much integrated luminosity as we can, it may be advantageous to back off the root S a little bit to get us to higher instantaneous luminosity. So this is a plot of instantaneous luminosity versus center of mass energy. And as you can see, as you kind of back off the maximum range, you increase your instantaneous luminosity. So if we can, so here's 140, here's a little above 100 in root S, and so we can think about, if we back off, say from 141 to 122, we cut off just this little bit of our kinematic phase space, but we potentially gain something like a factor of 2 or a little more than 2 in possible integrated luminosity. Our gains are larger if we back off even more to say 100. Then we're cutting off all of this stuff in here. And then I also show that if we go to, too low of energy, though, we're really maybe restricting ourselves quite a bit. So it's just something to keep in mind, playing off kinematic reach versus our ability to collect statistics. So I'm going to move away from that measurement now and talk a little bit about angularities. So I'm kind of now moving into the photoproduction region, and so Felix is going to talk about this stuff a little bit more. So I'll just go over it a bit quickly. So this is the inclusive jet cross sections in the photoproduction region. 10 to the minus 5 to 1. And here I've also changed my jet finding parameters a little bit, so I'll just mention we go down to a slightly smaller radius of 0.8, a more restrictive inelasticity cut, and now we're doing our jet finding in the lab frame. And at low Q squareds, the difference between your lab frame and your bright frame is more of just a boost along some direction, and so it doesn't matter as much. And yeah, so cross sections above 4 and 10 GeV, and so you see just the simulation we get out of PYTHIA is doing a reasonably good, is in reasonably good agreement with the theory curves, which Felix will describe more.
Okay.
Yeah.
Where is the proton? Is it negative side or positive?
The what?
The proton rapidity.
The proton goes to forward rapidity.
Positive.
Positive. Yeah. Yeah. So the proton is going in your plus rapidity direction.
Is it fair to say that some samples, let's say, a high positive rapidity, they come from like target fragmentation?
Maybe. I haven't looked at that explicitly, so I don't want to say yes or no, but yeah,
I just wanted to have like a cartographic picture of more or less where the jets are emanating. So naively in cities, in the hierarchy region, I will have events from target fragmentation. So maybe it's a stupid question, but the question is whether those samples in the hierarchy region, they do correspond to sort of current type of current process, or is it also coming from like a very nice? So is that plot completely isolating the sort of recurring fragmentation type of process versus what, or is everything?
Okay, that is a question which I think with jets is very different than with CDs. Because in CDs you look to one hard one and you can have low C and so on. Here now, if you would increase your PT, for example, for the jet, so it's an integrated plot which Brian shows. I have a hard time believing that a jet which has, for example, a PT of 15 GeV would come from a target remnant. Like Quark. Because that is the other thing, if it is inclusive jets, now you could ask, how does a jet which comes from a diquark look like compared to a jet from a quark? That is, of course, a very interesting question. And I don't think that anybody looking physics, Banner, whatever, you know, from these really people which know would have an idea how jets from quarks versus diquarks look like. It's an interesting question.
Because that can give also the footprints of what we expect to see.
Yes.
Kinemically, if it doesn't work for the jet, then
Sure.
I should not be looking at it.
True. And it's a very interesting question. And in the Monte Carlo, of course, you could look whether the jet is initiated by a quark or by a diquark or so on, and see the matching fraction. That is an interesting question to answer.
yeah, maybe we can talk and think of some. Yeah, because you know, in PYTHIA, I can just look through the record in some way and geometrically match my jet to whatever parton is coming off. So I can look and see, you know, this is my diquark propagating, you know, roughly down the beam pipe. Was the, you know, did it kick off something that then formed the jet? I can, in principle, trace that back.
Certainly, these are the class of flows that in principle are more useful for cities instead of seeing events. Just looking at the rapidity of the outgoing hydrogen, you know, to show that there is an actual separation.
But one thing which jets as well, of course, is that if you have a very high X interaction, so your parton is very high X, then the jet will go at this a very forward rapidity, so proton rapidity. Now a jet is a much better surrogate for the parton than, of course, a hadron. So I think the problem is much bigger for hadrons than it is for jets. So that is that's because you were asking. So I'm just, but absolutely a valid question and an interesting question to see whether there's something which you can find to separate diquark jets initiated by a diquark in quotations versus a jet initiated by the structure.
I think very early on, I think I looked at some of this stuff, but then kind of dropped it because I was seeing Dijet events that were arising from
DIS
processes, and I was, you know, where the hell are they coming from? And it was really the remnant that got us enough of a kick, the diquark that got enough of a kick to to bring a jet into my acceptance.
And
But it's certainly something I can go back and look at.
It's not some characteristic.
I'm not quite sure because I don't know how to, I don't
Well,
understand
your
enough for that
ICT
higher.
momentum has to travel through just more propagators to
Yeah.
go into the
Yeah. But
So
also,
should
I
I
would
ask
think the digest would be not so much back to back as in for PGF and QCD.
So this is inclusive.
Yeah, I know.
Yeah. And it's yeah, so I separate the resolved and then I just the direct is here.
It's including one jet like that.
So I mean it you know, if I have two jets in the event, I fill this plot twice. Yeah. Inclusive just means I don't consider them at the same time. Yeah, so maybe I'm out of time, so I'll just talk, you know, so we're also looking at substructure. One point I want to make is when we're thinking about jets at an EIC, there are some things you have to keep in mind. So there's this relationship if we're looking at an angularity quantity that like this. So this is the substructure variable we're looking at. This angularity is defined as 1 over the jet PT, and then you sum over the particles within the jet, and you weight them by their distance from the jet thrust axis to some power. If you take a to 0, your angularity should equal this quantity here, the jet mass squared divided by the PT squared. And when you're at very low PTs, what we found is that your individual the individual particles within your jet matter. So let's say if you're at like the LHC where you're at very large jet PTs, you know, if you have a neutron in your jet, you know, who cares? But if you're at a PT of like 5, you know, a neutron in your jet is a 20% effect. And so the first thing I saw when I made this relationship was that was this curve here. If I take this tau naught over this mass squared divided by PT squared quantity, it's very spread out, not peaked around 1 at all. And that was because just naively I was just adding up, you know, in PYTHIA I have the full 4 vector for each particle, so I was just adding them all up. And what we were seeing was that the mass of the actual particles was smearing out this relationship. If I just went through and then manually set all the individual particle 4 vectors have 0 mass, then I recover this this quantity nicely. And so experimentally, what this is telling me is that as I go lower and more in PT, these kind of mass effects become more and more important. I don't show the plot here, but if I made this plot for, say, jet PTs above 10, this curve starts to come in a little more peaked. This is just quickly about the detector. So basically, when we're measuring angularities, we want a very good EM-cal, good spatial resolution EM-cal. So basically, if I don't detect my photons, I move from this blue curve to this green curve. So, you know, good detector. Just a quick slide on Quark Gluon discrimination. It's one of the things you can do with these variables. You can see you get some separation. And since I'm out of time, I won't go through the detector stuff. Yeah, you guys. And then I'll just leave my summary up on the board.
Ryan, some quick questions. I was actually surprised with your results for spin asymmetry because somebody recently told me that the PYTHIA cannot compute anything related to spin effects. But you said that you just use the polarized PDF, polarized cross section. That's enough to.
Yeah, you just weight the events.
Is there anything missing? That's simple.
Yes, we do that all the time and it produces things very well.
So they revert by the Partonic
Yes.
asymmetry. So
It's all a leading order, but yeah, it's just you have the you flip to the back of Elliot Weaver's book and he has all the A hats for the various processes
Yeah,
that
but
depend on
you
your.
have the yield power. We discussed it with recently. You cannot create this related to.
True, because he doesn't have a Comac or whatever we want to call it, macro or Perl script, which takes the events from PYTHIA and has also included. So it's a bit of
So
work to code
PYTHIA
this all.
isn't
itself
doing any of
doesn't do
this.
this.
I take the knowledge, so I take the kinematics from PYTHIA and plug it into this formula, which gives me my A hat, and then the Q squared and stuff gives me where I should be sitting on the PDF, and I just make that ratio, and then if you weight each event by that, the average of the weights comes out to be area symmetry.
So that is exactly what we can also do for the Wigner functions. If we have the Partonic ones, then we can kind of generate also asymmetries. Absolutely. But we need to code that.
however, it's the showering. What about the showering?
Yeah, that was
Right. I mean, the showering is different.
Yes.
So how can you accommodate that? How can you account for that? Right. The showering comes with certain splitting functions. Primarily, they are the same, but they're not quite the same. So.
Yeah, that's not in
That's
there.
a concern,
Yes.
right?
Yes, so the shower, so this one is not taken into account because we don't have, and that is something which we have been saying since a while, we don't have a fully polarized Monte Carlo. It's even worse for transverse, where things are also suspended.
Yeah, right.
Can be different. So at the moment we use the unpolarized showers.
Anybody work?
9.
Yeah,
It's a lot of work, and so actually I should say there's a very positive trend that also Monte Carlo turbos lately have become much more interested to work again on EP. So maybe on the long run there is a chance, but right now there's no way.
Why is Ryan interested? Because of the EIC?
So
The GC or just because?
so the thing is, I think they have worked for years,
Beginning with
very,
the
very
LHC.
hard on LHC. And they have made an enormous progress, and I think that tails out a little bit. Let's say, and then there is a lot of new projects which involve EP. So the LHEC, the EIC, the VHEP, and they get more interested, which I think is a great thing. I really think that is a very positive development.
About fixed target applications.
But that
And
is
the
again
polarized-
proton.
Yes, but
the-
polarized.
Yeah. Yes.
Can you go back to this part of the movie?
This guy?
Yeah. So this small PT you got like two. So one question that I have is when I
So I'll stop you. I show everything down here, but really I should just cut the plot off at like 4 or 5. Anything below. So there is a question as to how low we can go, but I don't believe we can really go below 4 or 5.
one question that I have is okay, that four is in the jet.
I'm sorry, what?
So that four means let's say 4 particles inside of the jet.
Yes. So like say I'm at a PT of, say I measure a jet with a PT of 5. So you go up to this point and it's like, 5.5 or something. That's
Okay.
5.5 on average, 5.5 particles in the jet.
And what about in the full event?
Oh, that I honestly haven't looked at. I haven't made that. So you're asking if I find a jet with a certain PT, what is the global activity? I've never made that.
The only thing that a little bit concerned because this is PYTHIA is up to which extent downstream is working. Because I know that late, for instance, he told me that you need to have one particle per rapidity unit. So when I see a decrease of particles, of course, I'm looking at something inside the jet, so I'm asking what would be the amount of duplicities that you have outside of the jet. If that number, let's say, is, let's say 10, but it's not really.
So remember remember these are big objects. This is a radius of 1. So this jet extends for 2 units of rapidity. And 2 units of azimuth. So these are
So
big
4 particles per 2 units of rapidity. That's more or less.
Yeah, it's delta
Okay.
beta plus delta phi square root. That is what R is.
And I mean, those particles aren't guaranteed to be distributed evenly across the jet cone, but in fact they're not. But
Right.
Yeah.
So, but now one thing which yes, as always says PYTHIA might be not, and so on. True, but we have been using PYTHIA for 200 GeV in proton. We have done the studies for underlying event, which we hopefully publish soon, and PYTHIA agrees to 10% with all of what is in the detector. And we take, of course, a full detector model into account. So yes, if you want to have it precise to 1%, it is probably not. But I think for a lot of the studies right now for the EIC, it is very, it reproduces very well, because it also reproduces the HERA data very well. We have shown it produces a charm well.
it's actually this
The
plot here.
photoproduction well.
Oh, no. I'm not disagreeing on that.
Yeah.
I'm just saying that if I look at kinematics, like small PG, low energy, then the ability of PTF to sort of, for instance, I don't believe that PTF works at data.
It was also not designed for this.
Right, it's exactly. Lev always tells me I cannot look at that stuff. And he tells me, for instance, in E plus E minus, I cannot look anything below radius of 10 GeV. He said, no, you cannot go beyond that. So when I look at these numbers, I get, okay, we should extend these, these simulations in those corners of the phase space that if you go to really high energy, everything probably will work in simulation. But if there is any focus on those kinematic regions, thinking about transversion and everything,
So I'll say, yeah, with my experience with 200 GeV jets at Star, nothing I've seen here, like what I'll say, nothing that I've seen like leaps out at me and says there's some kind of breakdown here. Everything that I see from the EIC generally, when we simulate EP at 140 GeV, nothing really jumps out at me and says, this looks like something broke down and doesn't work anymore. And again, to what degree, it really describes what we'll see it in EIC, at what percentage level, fine. But I think for just in kind of, looking at things, getting a feeling for what's going on, I think this is more than adequate.
And
Okay,
particularly, just one thing, for the underlying event, it's small pt. Underlying event is soft normally. And that actually is also relatively well reproduced. So
I can
you
show
can
those
go to
plots. I
10
didn't put them in the
MeV,
talk.
maybe no, but the 100, 200 MeV particles are actually looking pretty good. Just as a,
Okay, let's thank Brian again. Coffee break. Felix Ringer also talk about